Yeah, got it. Yeah. Okay, so hello everyone. Welcome to this new seminar from the Instituto de Astrophysica. This is the second in a week. Today we have the pleasure to have with us Rafael Minogis, who will be talking about accretion, massive giant stars and black holes. And he will be properly introduced by Mayra, who is his host here.
Thank you for coming. It's a great pleasure to introduce Rafael Minogis. And Rafael is a postdoc researcher interested in accretion processes in various astrophysical objects, from young stars to black holes. And he's an expert in hydrodynamical simulation, massive star formations, and magnetic field. And Rafael is currently postdoctoral fellow at the Astroparticle as Cosmology Lab in Paris, working on pre-merger binary black hole. Before this, he did his PhD on massive star formation in Saclay, France, and defended his thesis in 2020 under the supervision of Dr. Matias Gonzalez. And an interesting aspect of Rafael's CV is that he has his own YouTube channel where he organized seminars about accretion and ejection process in star formation. I invite all of you to attend these seminars. So he is a true influence in this topic. Well, enjoy his talk.
Thank you very much, Mayra. So I don't need to introduce myself. We'll be talking about accretion in two different types of objects today. Massive star formation and binary black holes. In both cases, it's very important, but not for the same reason. For example, in massive star formation that I used to study during my PhD in Saclay in France, accretion is what determines the growth in mass of the massive star. So that's why it's so important. In the case of binary black holes, the purpose is not the same. It's not important for them. It's important for us to see and to observe those black holes, even if it's single black holes, but even more importantly, if it's binary black holes, because then we can predict what would be an electromagnetic counterpart to the merge of binary black holes detected in gravitational waves. So I will present the works I've been doing on these two topics, and between the two, I will show you how we can use the same techniques to address those two problems, which was also basically a personal transition to switch from one topic to the other. And I guess that some of you, and especially the PhD students, will learn something from such a scientific transition. So first of all, let's focus on the formation of massive stars. So why should you care about them? So we're talking about the stars that are more massive than typically 8 solar masses, but even more importantly, we're talking about very luminous objects, more than 10 to the 5 solar luminosities. Because of this, they exert a strong feedback processes on their surrounding. For example, on small scales, they hit their environment. They also inject, they transfer relative acceleration because of their high luminosity. On larger scales, because they have also warm atmospheres, they ionize their surroundings. That's what causes this formation of H2 bubbles. And even on galactic scales, when massive stars explode as supernovae, well, they enrich the galaxy in metals and they inject a lot of kinetic energy. So we're talking about very important objects. And to study their formation, naturally, just like the star formation process in general, it would be a multi-scale problem, but it's also a strongly non-linear problem because of these feedback loops. So that's why numerical simulations are quite important. What do we know so far? Well, what we know is especially what we know from low mass star formation theory, actually. We know that stars, they form in these structures called molecular clouds, in which there are some overdense clumps that are gravitationally unstable. That's what we call prestellar cores. So those cores will collapse gravitationally, and at the center, it will form a protostar or several protostars, whose further evolution will be driven by accretion and ejection processes. And if you follow this system long enough, you will obtain typically a planetary system. So already studying star formation is actually studying the initial conditions for planetary formation. Now, what is the difference between low mass and high mass stars? It's also the number of each of them. I really like this plot because it shows the number of each type of star for a given mass. And as you can see, massive stars are very rare. So that's also why it's more difficult to get observational constraints on their formation. Another difference is the multiplicity of massive stars. Here you have the multiplicity fraction and companion fraction as a function of the stellar mass, and it basically increases. Massive stars are much more often in multiple systems than low mass stars, and it would be very interesting to understand why. So one way to address the problem of massive star formation is to build on our knowledge on low mass star formation and wonder how similar would be low mass star formation and high mass star formation. There are several very important questions to address. For example, do massive stars accrete from their local environment, such as what we think low mass stars do, or do they accrete from larger scale inflow? So that's a very important question, but I will not treat it here. What I will focus on is, do low mass stars and high mass stars share the same accretion ejection processes? And what is the reason behind this trend that massive stars are very often in multiple systems? And naturally, to answer this question, first, what are the physics? What is the physics that control their multiplicity? So what you have to understand is that historically, people who investigated massive star formation, they encountered a problem which is due to the very high luminosity of massive stars. That's the so-called relative barrier problem. The thing is, you want to form a protostar, you're using a simple model, simple 1D model, so accretion is spherically symmetric. The problem is that above a given mass, because the luminosity increases with the mass, above a given mass, the relative acceleration is stronger than the gravitational acceleration. So basically, the accretion stops, and the problem is that it stops at a mass of typically 40 solar masses, while we know that there are massive stars as massive as more than 100 solar masses. Fortunately, multidimensional simulations, they have shown that anisotropic accretion could solve this problem. For example, here via an accretion disk, so that the relative pressure is released perpendicularly to the disk. So this solves the problem. We can form stars that are more massive than 100 solar masses. And the simulations, they have also shown the formation of relative cavities in which relative pressure dominates over above and below the disk. And some of them have also shown the formation of radiative Rayleigh-Taylor instabilities as a second mode of accretion on the edge of those relative cavities. Do we have any observational constraints of anisotropic accretion? Well, yes, we do, only in the form of accretion disks, especially thanks to a high angular resolution observations very recently. Here you have now a few examples of such a disk around massive protostar. There is also this review, if you want to take a look, by Beltran in 2020. So that's what we know about accretion. What do we know about ejection? Because the simulation, they show that that there were some relative cavities, also basically relative outflows. Well, when we take a look at the force in the outflows around a high mass protostar, so the force of the outflow is basically the momentum of the outflow divided by the lifetime of the outflow, it's typically 2 orders of magnitude higher than what would be predicted by a purely radiative launching. So that we know that outflows around massive protostars, they are just unlikely to be at least only relative. And something also quite interesting is that a significant part of them is monopolar. So many questions that we want to address. And what I focused during my PhD, well, starting from my PhD, was the origin of these accretion and ejection processes, try to go beyond the historical view in which relative effects were very important. And since I will study accretion, what does it tell me also about the multiplicity of those of massive star formation? And to go beyond the historical picture, what is the role of magnetic fields in any of these questions? So to begin with, I wonder how important are relative transfer effects for the accretion, or in other words, do relative Rayleigh instabilities really contribute to the mass growth of massive protostar? So to do that, I will model the formation of the collapse of massive prestellar core. So naturally, to follow the fluid, which is made of gas and dust, you need hydrodynamics to follow its motion, and self-gravity, because that's what drives the collapse of the massive prestellar core. And because we're talking about relative effects, we also need to treat radiation as another component, let's say, and radiation interacts with the fluid because it hits it, but also it exerts some relative acceleration onto the fluid. To do so, I will use the adaptive mesh refinement code Ramses, in which basically we can refine the cells of interest based on some criteria, for example, the high density region. So it's a very precious code when studying star formation. So I will follow the collapse of such a massive prestellar core of more than 100 solar masses. We cannot resolve the scales of the star, so we use what are called sync particles. That's how it's done in the community. So basically, it's a body that can move in the simulation, and it interacts only gravitationally with the fluid. And because it mimics a star, you can also mimic feedback processes such as the luminosity of the star. Naturally, by considering such idealized conditions, I forget about any interaction with the larger scales, but that's, let's say, numerical experiments so that we can address the question of these accretion and ejection processes with high resolution. So this is a density slice perpendicularly to the disk plane. You have a sync particle here at the center, around which there is a disk, which sometimes fragment and forms companion. And you see those nice relative cavities that were already found in the literature. Now the question is, do we see any relative Rayleigh instabilities? Why it's important is because the studies that have shown this mode of accretion, they show that actually it contributes to nearly half of the total accretion. After that, some analytical paper has shown also that the smallest perturbations were the ones that would grow the fastest, so that it's a question of resolution. And it's been a debated problem since about 10 years because of the question of the resolution. So basically, the team that used to get this instability used to say that the other team didn't have the right resolution, and the team that didn't get the instability used to say that the other one didn't have the right relative transfer method. So we tried to put everyone in the same team, and we used the right resolution and the right relative transfer method. And as you can see here, so the edge of the cavity is refined to the finest resolution. There is no Rayleigh-Taylor instability. And the reason behind this is because actually, although the shell is unstable to the instability, the time it takes for the instability to develop is actually longer than the time it takes for the gas to be advected through the shell of the cavity. So this works. It shows that actually only accretion via disk is observed, and basically relative mechanisms are not important for accretion, unlike what was thought historically. Then what about the ejection? Or in other words, are the outflows driven magnetically or relatively around massive protostars? So then we will need to proceed to a similar experiment, but this time including magnetic fields, so solving the equations of radiation magneto-hydrodynamics this time. And we want to answer this question in an unbiased way. So basically, we don't want either to underestimate or to overestimate neither the contribution of the magnetic fields nor the contribution of the relative transfer. The problem is that in the ideal MHD approximation, because of the flux conservation, here you have the magnetic field strength as a function of the density. Because of the magnetic flux conservation, the magnetic field strength just increases without any limits and up to unrealistic levels. So that in the low mass star formation context, for example, the first simulation that included magnetic fields in the form of ideal MHD, they actually found that no disk could form because magnetic braking, which is the transport of angular momentum via the field lines, it totally prevents disk formation, while we know that disks are present around protostars. So that one way to circumvent this problem is to include non-ideal MHD, or in other words, a non-perfect coupling between the fluid and the magnetic fields. And then in the same experiment here, the non-ideal MHD basically acts as a regulator of the magnetic field amplification, typically at disk-like densities. In this case, we use ambipolar diffusion, which describes the drift between the ions and the neutrals in the fluid, and therefore it acts as a partial decoupling between magnetic fields and the fluid. And by using this, we will not overestimate the importance of the magnetic fields. Second, we will use a so-called hybrid redshift transfer method that we distinguish what is the radiation from the star from what is the radiation from the dust, because one is in the UV, one is in the infrared. And because of this, basically, the interaction of this radiation with the dust, which is coupled via the opacity, well, it strongly depends on the frequency of the radiation. And if you consider only one single radiation component, on average, it will be in the infrared. And because of this, the relative acceleration will be underestimated by a factor of 100. So that we need to take into account such a relative transfer method. So using both of these of this method, I will follow the collapse of massive prostellar core once again, but including magnetic fields and also investigating the influence of turbulence. So to do that, we'll consider 4 simulations depending on the strength of the magnetic fields and on the strength of the turbulence. Starting from a non-turbulent run, I will increase the turbulence level so that it can be subsonic or supersonic. And at this level of turbulence, I will also have another simulation with a higher magnetic fields, so that I have a set of 4 simulations, 2 of them in which turbulence is subalvenic, so basically magnetic fields dominate, and 2 of them in which turbulence is superalvenic, so basically turbulence dominates. So to give you an overview of those simulations, so here is the non-turbulent simulation. Here in this plane, here in the outflow plane, so accretion only occurs through a disk. We have a single star and we have very large outflows. Then increasing the turbulence level, but increasing also the magnetic level at the same time, the outcome does not change much. We still accrete via disk, a single star, and large outflows. Then the picture changes when we include turbulence so that it dominates over magnetic fields. Because then we do not form only one star, but 2 stars, each of them having their own disk, and the outflows are much less extended. And if we increase even further the turbulence, once again, the system is a binary, and then the outflow is monopolar. So I will come back to this, but what we find in any of those cases is that accretion only occurs through a disk. We see outflows, but we see also an influence of turbulence. We'll come back to that. And we find that if magnetic fields dominate, the system is unitary. If turbulence dominates, we find that the system is a binary. So let's focus right now on the origin of these outflows. And to do that, we will compare what comes from the magnetic field, the Lorentz force, to the gravitational force, and what comes from the radiation, so the relative acceleration compared to the gravitational force. So when it's red here, it's in the outflow plane. Where it's red, it means that the outflow is driven by the Lorentz force. As you can see here, it's driven by the Lorentz force and by the relative force. But then when we compute the ratio of the Lorentz to the relative force, well, it's driven by the Lorentz force nearly everywhere. And even for a star that is as luminous as 10 to the 4 solar luminosities. We can decrease the resolution to integrate the simulation further and reach higher luminosities. And basically, the picture does not change much, except in the very close vicinity of the star. But everywhere else, it's all driven by the Lorentz force. That we find that the outflows around massive protostars, unless in the contrary of what was thought historically, it's driven by magnetic processes. What is this process? Well, we can decompose the Lorentz acceleration by the gradient of magnetic pressure. So this is this term. You recognize typically the gradient of a pressure. So what you would have in general with the thermal pressure gradient. Here, this is the magnetic pressure here, and the magnetic tension, but which is not relevant for this question. And what happens is that the field lines that are anchored in the disk, they will create a toroidal component as the disk is in differential rotation. And therefore, you have a toroidal component of the magnetic field in the disk, and this component is absent above the disk. So that it will create a vertical gradient of the associated magnetic pressure. And when we compare indeed the magnetic pressure acceleration to the gravitation, the magnetic pressure acceleration dominates nearly everywhere in the outflow. That's the so-called magnetic tower flow. There is also some hints of magneto-centrifugal acceleration, in which case the flow follows the field lines until it reaches the so-called Albin surface, which its velocity is equal to the Albin velocity. And actually, we have some hints of the presence of such an acceleration region up to the Albin surface. So we have results that are also consistent with the magneto-centrifugal acceleration, but I would put a warning because we need very high resolution to get converged results on this. What's quite interesting is that actually there have been some measures observations last year which actually confirmed for the first time the launching of magneto-centrifugal jets around a massive protostar. If you are interested, there is this paper in, I think that was in Nature Astronomy from Moscadeli 2022. So what we conclude on this part is that magnetic fields are important for ejection. Then are they important for the multiplicity of the system? Well, as you will see, yes. If we compare the magnetic field level and the turbulence level and see what is the outcome in terms of multiplicity, well, basically, when magnetic fields is dominated by turbulence, we get a multiple system. And when magnetic fields dominate over turbulence, we get a single star system. What is the explanation behind this is because the turbulence, which is basically the motion of the gas, it has some dispersion, it carries angular momentum. And the angular momentum just helps the disks to build, to increase their size and their mass, and therefore their self-gravity. And that's the self-gravity of the disk that will lead to its fragmentation and to the formation of a companion. On the other hand, magnetic fields, they remove angular momentum by outflows, by jets, also by magnetic braking, and therefore they reduce the disk size. So basically they have the opposite effect. And when you increase the magnetic field strength, you obtain in the end less fragmentation and a single star system in this type of simulations. What is once again quite interesting is that simulations and observations have now reached a resolution such that we can really compare the individual accretion structures in massive star formation, in simulation and observation. Here you have this paper by Tsikhanowski 2022, in which you have two massive protostars here, with each of them having its own accretion structure, although we would like resolution to really identify the protostellar disks. But the mass of the protostars, the presence of some filaments of gas between the two, and their orbital separation is very much in agreement with this type of simulations. Now comparing the magnetic fields not to turbulence but to the rotation, which is a paper that has been accepted actually yesterday in Astronomy and Astrophysics, we get basically the same results, and we wanted to really compare this time a case without any magnetic fields, so the purely hydro case, to the MHD case. And as you can see here, you have 4 stars. In this case, in most simulations, you have only 2 of them, and sometimes if you reach really high resolution, you can actually see the fragmentation of these small disks, in which case it forms a system of 3 stars. What happens here is that in the hydro case, you have the formation of very dense structures. Here you have a filament that links the 2 binary systems, and every time there are some spiral arms from each of these disks that collide with this filament, you can have additional fragmentation and the formation of a higher multiplicity system. actually this filament is just purely absent in the magnetic field case because the magnetic pressure just adds up to the thermal pressure, and in this region it leads to a much more diffuse filament between the two systems. So that's once again shows the effect of the environmental condition in the form of rotation, turbulence, and magnetic fields to set the multiplicity of stellar system. And in comparison, we can compare this run without magnetic fields to this one, which comes from the paper of Bate in 2018. The system is very much similar, as you can see here. And actually, what we show is that if you include magnetic fields, this type of system is unlikely to form because this filament between the two will be probably diffused by the magnetic pressure. So these are my take-home messages on this part, which is that on the accretion process, actually, relative effects are not important. Disk accretion is the only mechanism that we observe. The outflows, we find that they are mainly driven by magnetic processes. And we find that the multiplicity is mainly set by the environment in the form of rotation or turbulence, which increases this fragmentation, or magnetic fields, which impedes it. In any case, we find that, on the contrary to the historical picture, magnetic fields play actually a central role in massive star formation. And I will switch to my second part on binary black holes, and first showing you how similar are those two systems, and basically how I could make the personal transition from one topic to the other using the same techniques. So on the left, you have a massive protostar. On the right, you have a black hole. If you want to follow the accretion around each of those, well, you solve the equation of hydrodynamics, but in a gravitational potential. In some cases, cell gravity is more important, typically in star formation, than around, especially in supermassive black holes. But still, what's quite funny is that both of them are very much open in binaries. Naturally, for black holes, we now know, thanks to LIGO and Virgo, that binary black holes are very frequent system. And we also expect the growth of galaxies, the merger of galaxies, to lead to binary systems of supermassive black holes at the center, that we know that black holes are very often in binary systems. We know that accretion is magnetized, and I hope that I convinced you that it was very much important in the case of massive star formation. There is naturally some differences because in the case of black holes, the temperature is very high. So the medium does not have the same component, that it's very much ionized, so that ideal MHD approximation is fine in the accretion disk case of black holes. Not so much around massive protostars. But then what really makes the difference is that historically, the radiation is very important for massive protostars, while naturally, if you want to model an accretion disk around the black hole, the point is to describe the strongest gravity effects, and in this case, general relativity. So my work was to study the accretion around binary black holes. Why? Well, to try to predict what would be their electromagnetic counterparts. The idea is that to expect any counterpart from the coalescence of two black holes, you need them to be in a gas-rich environment, because otherwise they do not emit light. So that's why we do not have any evidence so far of electromagnetic counterpart of stellar mass black holes. But for supermassive black holes, we think that they will merge more or less at the same time as their galaxy, as their host galaxies merge, and therefore it should be in a gas-rich environment. Then what would be quite striking is that if we could detect the gravitational waves emitted by the merger of the supermassive black holes and their electromagnetic counterpart, we could basically witness the growth of black holes and galaxies at the same time. We could also compare the arrival time of the gravitational wave and the arrival time of the photons, and therefore constrain the speed of gravity. Is it really the speed of light, or does it deviate? And therefore naturally put some constraints on the validity of general relativity. And another question I'm very much interested in is that if we could follow, in particular, the pre-merger phase, then we could, in the end, witness the formation of a quasar or an active galactic nucleus, which would probably result from the coalescence of the two black holes. So that would be amazing. In 2030, and certainly some years after 2030, LISA will be launched, and it will detect the gravitational waves emitted by the merger of supermassive black holes. However, it will have some error box, which will be quite large in the sky. And the question for electromagnetic missions would be to scan this part of the sky and to be able to say, okay, no, this is a transient source, or yes, that's the binary black hole that we are actually observing with LISA. So my work is to try to predict what would be the electromagnetic signal emitted by binary black holes that could lead us to distinguish any binary black hole system from any other transient source. So to do that, I modeled the fluid around a binary black hole, and to take into account the gravitational influence of the binary, we use an analytical binary black hole spacetime that we have implemented into the code. The code needed to be extended to work with dynamical spacetime, because we're not only talking about strong gravity here, we're talking about orbiting black holes, and therefore the spacetime is not only strongly curved, it's also strongly dynamical. So that the numerical code I got to work with had to be extended for dynamical spacetimes. We implemented a spacetime of binary black holes in it. So that's very terrible. That's only one component of the metric. So for some of you who had some general relativity course in the master, you can remember that basically this and the first term is the Schwarzschild metric. So here this is this, and this is only contribution from black hole 1. So you have the same for black hole 2. So that's just terrible. You don't want to deal with that. That's just to show you that it's still quite computationally heavy construction, but still typically 10 times less computationally expensive than solving the full Einstein's equation to get the spacetime dynamically in the simulation. So here are the accretion structures that we find around a binary black hole. So this is the spherical grid. I mean, this is a cylindrical grid because it's 2D, but what I mean is that in the inner boundary of the simulation, you have the two black holes here that are rotating in circular orbit around each other. What we find is that there is the formation of a cavity, a low density cavity around the binary that was predicted actually in 94 already analytically. There are also some strings that follow the binary. So all of this was predicted. What is quite more surprising, I will show you the movie now, is actually the formation of a strong asymmetry that you will see appearing. This is very surprising. We're talking about a simulation in which everything is symmetric at t equals 0. The two black holes have exactly the same mass, and you end up with an asymmetry on one side. And this asymmetry, which is called the lump, which is what you, when you are doing crepes, that's what you call, so it's grumeaux in French, so that these over densities, it's been called the lump for 10 years, and there was no real model to explain how it formed, although it was seen in all the simulations. But actually, any of these structures could be actually the key for a pre-merger electromagnetic signature. So we try to investigate a bit further what could be the origin of the lump. So to do that, we plot on the right the radius as a function of time, and we plot the density along this radius, which is basically along this line. So the fluid will just move around, and we will just plot the density, which is along this line. What is the point? The point is to see all the periodic features from the simulation. For example, all the diagonal lines that you see here, those are the spirals and the strings that you see closer to the origin. What happens is that after some time, you see that it's no longer symmetric between the left and the right. You see appearing this lump as this overdensity from one side to the other, which orbits at several times the orbital period. What we found is that actually it shows up as an instability because of an exponential increase, and we proposed a model for this, which is the so-called Rossby wave instability, which we believe that occur at the edge because of the very strong gradient of density at the edge of the circumbinary disk it's unstable to this hydro instability, and that's what we think is causing the lump. But then going back to our electromagnetic counterparts, can we say something about them based on those accretion structure? Well, yes, but we need to produce synthetic observations out of these simulations. And for that, we use the ray tracing code Giotto, incorporating the same binary black hole metric, so that actually the pipeline, which is formed by our fluid code and this ray tracing code, the two of them, which work with the dynamical spacetime, and in particular with the binary black hole spacetime, it's actually the first so-called numerical observatory in Europe. And it follows its, let's say, its counterpart, which has been developed in the US in 2018. Then we will use some simple approximation for the emission of the fluid, typically thermal emission, and use some scaling laws based on sources that we already, for which we already know the typical temperature of the disk and the mass of the central black hole as reference, and then some scaling laws to get some physical units out of our numerical simulation. So that's a typical emission map from the circumbinary disk around a binary black hole. What we want to see is what is the impact of the accretion structures on the synthetic observations, and whether it could be used to distinguish binary black holes. So on the top, you have the accretion rates through the cavity as a function of time, which varies on very short time scales. This is actually the period, the semi-orbital period of the binary. And on the bottom, you have the flux, the electromagnetic flux of the circumbinary disk. And this is varying by typically 15% on much longer time scales. Like actually the modulation which is produced by the orbiting lump. What's interesting is that here we are talking about a flux which is actually normalized by the mean flux. So that's this plot is independent of the mass, of the total mass of the binary black hole. Then zooming on one of these modulations, taking different mass ratio, different orbital separation, just to show you how universal are those results, we find that on top of the strong modulation because of the lump, we have also so much tinier modulations which are produced this time by the spiral arms, and therefore they are modulated at the semi-orbital period. So that to conclude on this, we have been able to develop a pipeline which produces fluid simulation and synthetic observation in dynamical spacetime, in particular in spacetime around binary black holes. We have identified some structures of interest that were already found in the literature, and some of them even predicted analytically more than 20 years ago. We also proposed a model for the lump. And what we find, because that's the final question we're interested in, what we find is that there is a 2 time scale modulation in the light curve between which is produced mainly by the lump and on shorter time scale also by the spiral arms. So that's all I wanted to tell you about this, although everything scales with the black hole mass. So that knowing the black hole mass is very important because all the time scales are proportional to the total mass of the binary. Then something I have not mentioned is that in those simulations, we initiate the gas distribution with a circumbinary disk, which is already present. The question is, do we know what circumbinary disks in the universe look like, actually? What's interesting is that the lump I mentioned is absolutely not a GR effect. It was seen even in the absence of general relativity in the simulation. And what's even funnier is that people claim having found a similar lump feature. So actually in the black hole community, we call it the lump. In the planetary community, they call it the horseshoe feature. But that's quite striking. These are observations, actually. And my final message for you will be actually a question is, could we use the new constraints we have on circumbinary accretion to actually further constrain the initial conditions of the simulations around binary black holes, and therefore to identify what would be the electromagnetic counterpart with more realistic circumbinary accretion models. And that's all for me. Thank you.
Thank you, Rafael, for this nice talk. Actually, two topics in the same seminars.
Yeah, sir.
And now it's time for questions. If you have the audience ask questions, I have a lot, but I prefer you ask some question, or perhaps people in the Zoom. Well, let me start. We had here in our institute a very strong group studying taking pictures around black holes. Actually, we had a picture of black hole of our galaxy. And the picture looks like protoplanetary disk face on with a central cavity. But something that brought my attention from the talk is the overdensity of lumps. Do you believe that we are perhaps in the lines to detect this overdensity in black holes also?
So I think that that's typically formed by the binary. So it's not the fact of having a single black hole, it's the fact to have a cavity. The cavity leads to a strong decrease in density, so that the zone, the edge of the circumbinary disk isn't stable to this instability. So that's something that is really linked to the fact of having a binary black hole, or possibly just a binary. For example, in this case, this is a star and a planet, but even if the mass ratio is smaller than 1, so if you have even two different objects with a factor of 10 of mass between the two, it's still possible to form the lump. At least numerically, it's still possible. So there is no reason for this lump not to be due to the presence of a binary at the center.
Thank you, Rafael, for your talk. I have a question on something you said about monopolar outflows. You showed that monopolar outflows could be produced in binary systems. So my question is whether you know if it's physically possible to reverse the direction of the monopolar outflow, or is it always in the same direction?
Yeah, sorry. So I think I was not clear enough on this. I tried to. I had actually I have a slide on this, but what I meant to say, it's not that it's due, although it's at the time where there is a binary system. It's not due to having a binary. It's due to the fact that when you include turbulence, so these are the same simulations, but here for example you have the density. So you see for different turbulence and magnetic fields level, what are the type of outflows that you have. The thing is that even in this case, for example, the outflow is not monopolar, although you have a binary. The thing is that if you increase the turbulence, it adds ram pressure, basically dynamical pressure, and the outflow needs to overcome this pressure to be launched. And that's also, I think, a reason why in the simulations of giant molecular clouds that are done usually in the literature, where they try to study the formation of tons of systems at the same time. In general, these simulations are very much turbulent, with a Mach number of up to 10. There is no outflow. And I think that here I'm just at the transition between having an outflow. Here, in this case, turbulence is subsonic. In this case, turbulence is supersonic. There is a factor of 4 here between the two velocity dispersion, and there is no bipolar outflow, only a monopolar and transient outflow in this case, because the ram pressure is just too strong. So it just makes it more complicated for the outflow to be launched.
Okay,
thank you, Rafael, for this impressive talk, taking two very different topics, trying to find out the similarities and the differences. My question is regarding the formation, also the formation of binaries. So you consider just a single isolated clamp, let's say, and then you find that the formation of a binary or even multiple system is determined by the turbulence and the magnetic field both. And you compare your results, for example, with the results of Bay, and I remember he uses a cluster of stars. So you only consider for the formation of binary the disk fragmentation mechanism,
but you can have a fragmentation of the core itself at larger scales, which is supposed to form wider binaries. And also you can have, if you have a cluster, you can capture a binary. So how this affects your result, because they are strictly similar to the ones of Bay.
Yeah, you're absolutely right. So by considering massive pre-stellar cores that are isolated, basically I just focus on disk fragmentation. So I'm not saying that core fragmentation is obviously occurring in the universe, but I'm more focusing on if we change this physical ingredient, how does it affect disk fragmentation? And we also know that disk fragmentation is actually observed. We have some observation, for example, by Johnston, who in 2015, for example, with a quite massive disk, we see the spirals. So we see the hints of self-gravity of the disk. So this disk could lead to fragmentation. So we know that it's a process. We don't know which of the two, disk fragmentation or core fragmentation, contributes the most to the formation of multiple systems. But in my numerical experiment, just focusing on disk fragmentation, I found that changing the turbulence, the rotation, or the magnetic fields changes a lot the outcome. Then for the core fragmentation, I cannot say much, except that in general, if you increase the magnetic fields, you increase the magnetic pressure, and magnetic pressure is also found to prevent core fragmentation as well, to stabilize the cores.
I have a curiosity question, fully outside from my field, but I have seen these impressive movies of the black hole at the galactic center, at the center of our galaxy, and there is something that rotates. That see some similarity with your lamp. So I don't know if this is something which is similar, is the same phenomenon, or it's something completely different, an optical illusion.
Actually, that's something we thought about when we saw the images from the Event Horizon Telescope. You see the three blobs. Actually, some simulations of disk around a single black hole show also the formation of the Rossby wave instability. Because in the case of the binary, you have a density gradient formed by the binary. So it forms a cavity, then a density gradient, then the Rossby wave instability. For a single black hole, you also have a last stable orbit. So what is called the ISCO, the normal stable circular orbit. And below this radius, you don't have much material. So basically, you have quite the same cavity around a single black hole. That's the edge of a single black hole disk is also unstable to the Rossby wave instability. Now, what is the reason why we don't compare too much is that actually the Event Horizon Telescope, we are talking about integration of, if I'm not wrong, few hours or so, and compared to the dynamical time at which it would orbit such a lump in our simulation, I think it's quite difficult to compare. I think the three blobs for sure do not correspond to three blobs that we would see in an instantaneous simulation. We will need to integrate that for a few hours, and I'm not even sure that it would be comparable at the end.
Thank you very much.
Can I comment?
Okay.
I also was intrigued by that. But I mean, first of all, it's a binary effect, and it's not a binary our black hole. I mean, this would be extremely surprising. I mean, there's still some phase space left, but I don't think it's binary. The other thing is we don't have a disk around the black hole. So this is disk physics. We don't have a disk. We have some weird accretion flow around it, but we don't have a disk.
So we are sure it's not a binary.
I would bet a lot of bottles of trying to get the disk.
Thank you.
Francisco?
Yeah, there is one question in the Zoom chat. I will read that. So, hello, Rafael. Thank you very much for this nice talk. I wonder if you see your simulations, especially for high mass prototypes, one jet per accretion disk, or you have one main jet for the circumbinary disk. Thanks for support.
I really like this question. So what I see is that it's biased. So I think that what I see in those simulations, and that's also what I want to focus a bit more on what can create circumbinary disk, is that I don't see a circumbinary disk. What I find in the simulations of binary protostars, I see that each of the two forms its own protostellar disk, but there is no circumbinary, let's say, stationary or structure at equilibrium. That there is no way to launch a common outflow, because what you need to do is basically to organize the magnetic fields, have the proper conditions, and then it will launch the outflow. But if you have something that is very much dynamical, with this is basically in full motion. If you forget about the two protostellar disks, this is in full motion, that it will not create the proper structure for launching an outflow, and therefore the only outflow I see is from each one of the protostars. But linked to the question of Ruben, is that actually what are the conditions under which we form or we don't form a circumbinary disk? And I think that's a very interesting question.
Concerning the relative part, at the beginning of your talk, you said that the radiation might not be important, not important as magnetic fields or turbulence. But did you treat radiation like a pressure, or did you account for also heating, relative heating?
Yes.
Okay. As far as I know, this should prevent photo fragmentation, right?
It can. I didn't do a comparison of having the radiation and not having the radiation, and what would be the structure of the disk. So I think that, yeah, possibly it heats up the disk so that you can it can prevent to some extent the fragmentation of the disk. That's true, but I couldn't say. But for sure, yes, we model radiation basically just as a different component. What we do is we solve the hydrodynamical equations. We solve something that is very similar to the hydrodynamical equation, but considering a fluid which is made of radiation. That's the typical approach. And we consider two fluids, the one that is associated to the radiation from the protostar, typically the UV, and another fluid, which is, let's say, the environmental radiation, which is typically the infrared. But I think that, yes, you're right, there has to be certainly an effect, because it hits the disk, it can prevent the fragmentation of the disk. But I mean, what I meant with this question is that it does not change the accretion mode. We accrete with the disk with and without radiation, and we don't have radiative related instabilities, so that the only accretion mode we observe is through a disk.
Okay.
Although it's true that adding heating could change the disk properties. This is true.
Perhaps in later stages, when there are a lot of specific stars in the cloud, I mean a huge cloud, not only a cloud, then this effect should be accounted for.
Yes, and certainly something that you will mention in your talk next week is that photoionizing radiation, which we did not take into account in this study, because also we stopped at about 20 solar masses. But over 20 solar masses, certainly photoionizing radiation will play a role, and then it could play a role on the disk and also on the disk of several companions. And this is absolutely true. And that's actually something that I would like to do if I had continued in this way.
Well, more questions? I guess we have time for more questions. Let me ask another question for the first pass. I have curiosity about Ramsey's score about the physical conditions. I mean, which is the density that you assume. I have seen that you assume a density for the initial condition like goes R 1.5, but I'm wondering if you can change this initial condition, and also if you can say a few words about the opacities that these codes assume.
Yes, so we use some opacity tables. As people who work on the interstellar medium, we know that opacity is just somehow it's very much complicated. It varies through several orders of magnitude. What we use in this simulation, just like it's done in general in the literature, is to have some opacity tables that tells you for a given frequency what is the opacity of the mixture, which is made of dust, of gas. And for the initial conditions, yeah, actually, so we can change it. Here is one of the R to the out to the two. I think that in the first one, it's 1 over R.1.5. This is something we can freely change. For example, for this study, because I wanted to focus on the Rayleigh-Taylor instabilities, I took the exact same initial conditions as the people who found the instability to form. And in the second one, I just used the same as our previous paper, which was made by Benoît Commerson. So just to not to change everything at once, but just trying to increase incrementally the physics in the code without changing the initial conditions, because then we don't know how to compare.
Great. Well, if you don't have more questions, thanks again to Rafael.